Chapter 3, Internal Energy and Enthalpy. Section 3.4, the Joule-Thomson experiments. In the previous section, we studied the Joule experiments, in which a real gas expands against vacuum. In this experiment, Q is 0, W is 0. Therefore, delta U is 0. The internal energy of the real gas is held constant. In that experiment, the Joule experiment, we were able to study how the internal energy depends on the volume. Now here's the Joule-Thomson experiment. It's a collaboration between Joule and Thomson. In this experiment, the enthalpy of the real gas is held constant, and we call that isenthalpic condition. This comes from enthalpy isenthalpic. This isenthalpic condition is realized in this simple experimental setup. So we have a pipe, and on the left hand side of the pipe we have a real gas with pressure P1, V1, T1. Between the left hand side and right hand side there's a porous plug, so the gas can pass through this plug. Now we have two pistons, one piston here, another piston here. Right now we will just slowly compress this real gas from the left hand side and allow the gas to pass through this porous plug. Alright, so this is the initial state of the system, and this is the final state of the system. We make sure on the left the external pressure is P1. On the right hand side the external pressure is P2. And in this experimental setup we will prove that the enthalpy of the real gas remains constant. So first, let's look at the work done to the system. On the left hand side, work is equal to negative integral P external dV. P external is set to P1, so we have P1 here, and then we have the integral of dV from V1 to 0. We evaluate this because P1 is constant, then W1 is P1 V1. This is a positive because on the left hand side the work is done on the system. Now let's look at the right hand side of the pipe. Well, W2 is also negative integral P external dV. We just make sure this P external is equal to P2, and then we can evaluate this integral. The result is negative P2 V2. Now you may ask, if this P external is equal to P1, how can we compress the gas? Well, how about this? We'll just make sure this P external is greater than P1 by an infinitesimal amount. And over here, same here, this external pressure is smaller than P2 by an infinitesimal amount. And therefore we can assume this is this numerical value is just P2, and this numerical value is just P1 when we evaluate W1 and W2. So overall, work is done on the system on the left hand side, work is done by the system on the right hand side. The total amount of work is P1 V1 minus P2 V2. We need to sum this up. And because delta U is equal to W, I forgot to mention the entire pipe is well insulated. There's no Q, so Q is 0 for the system. There's no heat transfer between this gas and its surroundings, and therefore Q is 0. Again, Joule and Thomson made sure that there's no heat flow between this real gas and its surroundings throughout this entire experiment. So if Q is 0, delta U is equal to W. Therefore, U2 minus U1, that's delta U, is equal to W. W is P1 V1 minus P2 V2. Now we rearrange this equation. We can move this minus U1 to the right hand side, minus P2 V2 on the left hand side. And now we have this U1 plus P1 V1 is equal to U2 plus P2 V2. And remember the definition of H is just U plus PV. And therefore we have H1 is equal to H2. The enthalpy of the initial state is equal to the enthalpy of the final state. the enthalpy of this real gas remains constant after this real gas is pushed through this porous plug. And then we will evaluate this integral, this derivative, delta T over delta P, under this isenthalpic condition. That means constant enthalpy. We will again use the triple product rule in calculus and also the reciprocal rule. The triple product rule gives us this equation. We have h over p, p over t, t over h. The result is -1. Do pay attention to the subscripts. When we do delta h over delta p, t has to be the subscript. When we do delta p over delta t, h has to be the subscript. And when we do delta t over delta h, p has to be the subscript. We need 3 variables, 3 terms, and the product is -1. And therefore, we can evaluate this delta h over delta p on a constant temperature condition. It's equal to -1 divided by these 2 terms. So I'm copying these 2 terms here. And now we keep this negative sign here, and then we flip this to be delta t over delta p. We flip this to be delta h over delta t. And also, we need to make sure the subscripts. So over here, we have subscript h, subscript h, subscript p, subscript p. So when you use the reciprocal rule, make sure the subscripts are the same. And then this part is simply Cp. Delta H over delta T on a constant pressure condition is simply Cp. There's a reason delta H is equal to Q sub P. And then we have this expression, delta H over delta P on a constant temperature is equal to -Cp times delta T over delta P under the constant enthalpy condition, or isenthalpic. Over here, this is just one-line derivation that shows you delta H over delta T under constant pressure is indeed Cp. It's a little tedious because you need to expand this H to be U plus PV. And delta U is delta Q plus delta W. And delta PV is P delta V plus V delta P. Because pressure is constant, this part is just 0. And because it's isobaric, delta W is simply negative P delta V. And we have negative P delta V here, positive P delta V here, so they cancel. So these 2 terms cancel. This term is just 0. And then we have only the first term, delta Q. And we have delta Q over delta T, that's heat capacity. So over here we have the isobaric heat capacity. And now we have this expression. Okay, we showed you this expression. Now we're going to define this delta T over delta P under constant enthalpy condition. We name this Joule-Thomson coefficient in honor of both Joule and Thomson because they designed this experiment. Alright, so this is Joule-Thomson experiment under constant enthalpy condition. How does temperature depend on pressure? And we can see this term is equal to negative delta H over delta P over here, this one, divided by Cp. Okay, and there's a negative sign here. Again, this is Joule-Thomson coefficient. Why is this important? Well, if we kind of just produce this Joule-Thomson experiment with this isenthalpic condition, and somehow we can change the temperature of a real gas by changing its pressure. And if this is a positive number, we can drop the pressure of the gas significantly to drop its temperature so much that this gas can be liquefied. The temperature of the gas can be decreased to below its boiling point. And this way we can liquefy a real gas. So that's why it's important. Again, if this is non-zero, and then we can look at the sign, whether it's positive or negative. If this is positive, then mu jt is negative. If this is negative, then mu jt is positive. So it's really important for us to realize this Joule-Thomson coefficient, mu sub j hyphen t, and this delta H over delta P on a constant temperature condition, they have opposite signs because this isobaric heat capacity is always positive. Now let's look at the analytical expression of this Joule-Thomson coefficient again. Joule-Thomson coefficient is defined to be delta T over delta P under constant enthalpy condition. And by using the triple product rule, this is equal to negative delta H over delta P over Cp. So again, this is important because somehow we can change the pressure of a real gas to change its temperature. If the temperature of a real gas drops significantly, it's possible to liquefy the gas. Now let's evaluate this delta H over delta P. So first, delta H over delta P under constant temperature condition is V minus T times delta V over delta T. And we will be able to prove this after chapter 5. For now, we'll just evaluate this for a Van der Waals gas. For Van der Waals gas, we use Van der Waals equation. P is nRT over V minus MB minus AN squared over V squared. There are two parameters, A and B. They are Van der Waals parameters. And A is the measure of the attraction. B is the measure of the size of the real gas particles. And B also represents the repulsion between those gas particles. We will be able to kind of evaluate this for the Van der Waals gas. Oh, by the way, if you evaluate this expression for ideal gas, it's going to be just 0 because delta V over delta T is simply V over T for ideal gas. And these two terms cancel for ideal gas. So for ideal gas, H does not depend on P under constant temperature condition. Under constant temperature condition, H is a constant for ideal gas. Therefore, that's why we cannot liquefy an ideal gas, but we can use this to liquefy a Van der Waals gas. Now let's look at this. We need to kind of evaluate delta V over delta T. It's pretty hard to do. So we're going to evaluate delta T over delta V first and then take its reciprocal. So first we can express temperature in terms of volume. So this way, all right. How do we do this? Because we can see temperature only appears here, so we can have both sides plus AN squared over V squared. So we can move this to here, and then both sides multiplied by V minus MB divided by NR, and then we get this expression. So anyway, this is the analytical expression of temperature of a Van der Waals gas in terms of pressure and volume. Okay, we went from this equation to this equation. And now we can take its first derivative with respect to volume on a constant pressure condition. That means we'll treat this pressure as a constant, and then we take its first derivative. We copy 1 over nR here, and then, well, we have a product of two terms. So what we do is we use the product rule in calculus. What's the first derivative of this guy? Well, it's this. We copy N squared, and then this is V to the power of negative 2. Its derivative is negative 2 times V to the power of negative 3. So we get the first derivative multiplied by V minus MB. And then we copy this here. We take the first derivative of this part, which is just 1. So we have this expression. And also, because pressure is simply nRT over V minus MB minus AN squared over V squared, we replace this pressure with this expression. The only goal is actually to simplify this, because in P we have minus AN squared V squared. Over here we have positive AN squared over V squared. So if we add this two, we get this. Now we expand this product. We expand this expression. We get three terms. 1, 2, 3. We have three terms. This is delta T over delta V. And look, we have delta V over delta T here. Eventually, we'll have to take the reciprocal of this expression. However, it's really tedious to just take the derivative of this and then plug it in. So we're going to make approximations. We will make some reasonable approximations so that we get a fairly simple expression for delta H over delta P. And then we can plug it in here. We determine the expression of mu JT, the Joule-Thomson coefficient. And then we understand how can we change the pressure to change the temperature of a real gas. All right. And again, we'll make approximations, and then we will eventually prove delta H over delta P on a constant temperature. As V minus T times delta V over delta T is roughly this. And again, this is delta T over delta V on a constant pressure condition. This is delta V over delta T on a constant pressure condition. So this term and this term are reciprocal to each other. Now for a Van der Waals gas, again, we have this expression for delta t over delta v, and eventually we'll have to take the reciprocal, so it's complicated. We need to make approximations. What I will do is I will simplify this under two conditions. The first condition is this: I'm going to assume a is negligible, or simply a is 0, and then we evaluate this term. And then I'm going to assume b is negligible, and we will evaluate this term. Alright? And then this way we can somehow just simplify the expression of delta h over delta p or c. Now first, let's say a is negligible. So this first term is 0, the second term is 0. Delta t over delta v is simply 1 over nr times this part. Nr and nr cancel, so delta t over delta v is t over v minus mb. It's a lot simpler. And then delta h over delta p, we will evaluate this based on the assumption is negligible. So we have this is equal to v minus t times the reciprocal of this. Alright, so the reciprocal of this is simply v minus mb over t. We plug it in, alright, and then we get mb. This is simple. If a is negligible, h depends on p. The dependence is just mb. That's actually the space taken up by those real gas atoms or molecules. So it does have a physical meaning. What if b is negligible? Let's look at this. If b is negligible, we keep this. B is negligible, so this part disappears. If b is negligible, this part becomes nRT over v. So we still have two terms, but they look a lot simpler than this. Alright, so we have this copied here, and over here we have this nRT over v. Because b is 0, we get this expression. Now we will evaluate delta h over delta p. It's just v minus t times delta v over delta t. And this is just the reciprocal of this, so I'm going to put the reciprocal of this here. It's 1 over this, and then times nRT. The t comes from here, nr comes from here. Alright, we need to take the reciprocal of 1 over nr, therefore it's just nr. So this does look very complicated. We will simplify this a little bit. Alright, so first we're going to use this v as the common factor. And then we have 1 minus this guy, and on the bottom, okay, we need to multiply this by v. We need to multiply this by v, so we have these two terms. Alright, and we can further rewrite this by dividing the top and bottom by nRT. The top divided by nRT is 1, the bottom divided by nRT is 1 minus this, so we get this expression. And then we further evaluate this subtraction. 1 minus this is simply this guy. Alright, this is negative because this is 1 and this is smaller than 1. Okay, this is smaller than 1, this is 1. I'm sorry, this is greater than 1 because the denominator is smaller than 1. So this whole fraction is greater than 1. 1 minus a number greater than 1, we get a negative result. So this is negative. So from here to here, it's just algebra and it's negative. And now we're going to make some approximation again. So if you look at the bottom, it's 1 minus 2an over VRT. If a is small enough, actually for real gases, usually a is small enough so that 2an is much smaller than VRT. And therefore this fraction is much smaller than 1. For example, this can be 0.01. And then we're going to make approximation. 1 minus 0.01 is roughly 1. Alright, only because this 2an is usually much smaller than VRT. Alright, for that reason. And then we can say this is roughly 1. We can have this expression. V and V cancel. We have negative 2anRT. Very important. If B is negligible, only A plays a role. So H depends on P. The dependence is proportional to A, and it's negative. Now let's look at here. When A is negligible, H depends on P. The dependence is MB. When B is negligible, H depends on P as well. But this time, the dependence is negative 2an over RT. This is proportional to B. This is proportional to A. This is a measure of repulsion. This is a measure of attraction. Repulsion is positive. Attraction is negative. And now we made two different approximations. When A is negligible and then when B is negligible, what if neither is negligible? We're going to assume delta H over delta P is then this plus this. Okay, the repulsion factor plus the attraction factor. Alright, so it's going to be NB minus 2AN over RT. Again, when A is negligible, delta H over delta P is NB. When B is negligible, delta H over delta P is roughly negative 2AN over RT. When both A and B play a role, we're going to assume this delta H over delta P is the sum of NB and negative 2AN over RT. Now we have this Joule-Thomson coefficient, mu sub J hyphen T as delta T over delta P. It's negative delta H over delta P over CP. This equation comes from the triple product rule in calculus. And then the expression for delta H over delta P in terms of A and B is this. Now both the top and bottom divided by n, the number of moles, we get this. It's going to be just 2ART minus B on top, CPM on the bottom. So now we can say this. Mu JT can be positive, 0, or negative. If 2A over RT is greater than B, mu JT is positive. If 2A over RT is equal to B, well, mu JT is 0. If 2A over RT minus B is negative, then mu JT is negative. Alright? So it's more common for mu JT to be positive. So we'll study this case. Mu JT can be negative if the attraction is really small, the repulsion is really large. This is less common. But anyway, if mu JT is positive, then somehow we can lower the pressure of a real gas to lower its temperature. Here is one numerical example. Alright, we will examine the nitrogen gas given its van der Waals parameters A and B. We also have CPM of nitrogen, roughly 3.5 R. Now we're going to use this expression mu JT is delta T over delta P, and over here this is from the triple product rule. And then delta H over delta P under constant temperature condition is 2AN over RT minus NB. And then we simplify this by dividing the numerator and denominator by n. And then we can plug in all the numbers. 2A over RT minus B over CPM, which is 3.5 R. We plug in all the numbers. I think I have been using the SI units. So in the end, this number is in the SI units, 2.47 times 10 to the power of negative 6 Kelvin per Pascal. Both Kelvin and Pascal are SI units. We can convert it to 0.247 K per bar. Bar is not a SI unit, but using bar is sometimes more convenient than using Pascals. Alright, so what does that mean? That means, well, if you increase the pressure of nitrogen under the isentropic condition, its temperature is going to go up by 0.247 Kelvin. What if you decrease the pressure of the nitrogen gas? The temperature will decrease. What if you start with, for example, okay, 100 bar nitrogen at room temperature, and you change its pressure from 100 bar to 1 bar? Then the pressure drop is going to be 99 bars, and 99 bars times this, well, approximately you can decrease the temperature of this nitrogen gas by 25 Kelvin. And actually that's fairly significant. You know, if you can drop the temperature by 25 Kelvin, it's almost like from the room temperature to 0 degrees Celsius. I mean, you can feel it, right? And what if you can drop the pressure of nitrogen from 500 bars to 1 bar, and you will see more significant temperature decrease. Alright, again, we get this number in SI unit, this number in non-SI unit. Both values are positive. Well, that means When pressure goes up, temperature goes up. When pressure goes down, temperature goes down. All right, and this is positive because this attraction term is greater than the repulsion term. Numerical example 3.4.2. This time we'll look at a hydrogen gas with its A value, B value, and CPM. And similarly, we do this kind of calculations. We're plugging all the numbers in as a unit. This time we get a negative number. It's a negative 2 times 10 to the power negative 7 Kelvin per Pascal, or negative 0.02 Kelvin per bar. So actually this is negative. I just want to remind you, actually this mu GT coefficient can be negative. Why? Because sometimes the attraction term is smaller than the repulsion term, and then in that case this mu GT can be negative. It's a very small negative number. That means, well, if you drop the pressure of a hydrogen gas from 100 bars to 1 bar, although the pressure decrease is very large, 100 bars, its temperature change is fairly small. It's only 2 Kelvin based on this number. All right, it's only 2 Kelvin based on this number. So why does this temperature change? When pressure changes. So we can do a qualitative analysis. When pressure changes in this Joule-Thomson experiment, the volume changes actually. So when pressure drops significantly, the volume increases and the distance between the gas particles increases. That means you have to overcome the attraction. So if the attraction is large enough, you need to convert a great deal of kinetic energy to attraction. Well, and then in that case, part of the kinetic energy is transformed into potential energy. You have lower kinetic energy and therefore lower temperature. The temperature decreases. But in this case, in the hydrogen case, actual repulsion is like more significant than attraction. So in this case, when you drop the pressure significantly, you increase volume, and then that plays a role in the change of both attraction and repulsion. All right, but because the repulsion is predominant, actually you're going to have a smaller repulsion. When you have a smaller repulsion, well, the potential energy decreases. But energy cannot be created or destroyed. So where does this potential energy go? It goes into kinetic energy. So the kinetic energy increases, the temperature increases in this case, but not by much, okay, by only a little bit. Usually, okay, mu GT is positive. Okay, it's rare to have a negative mu GT. I'm just trying to show you a rare example over here. Now let's use this Joule-Thomson phenomena to cool nitrogen gas to a temperature below its boiling point so that we can liquefy nitrogen. Actually, this is how the industry make nitrogen liquid. For the nitrogen gas, the Joule-Thomson coefficient is roughly 0.247 Kelvin bars. Then it gives us an idea. What if we have a nitrogen gas with a huge pressure at room temperature, and then we drop its pressure to only 1? That way we can significantly drop its temperature, to below the boiling point, and then we have liquid nitrogen. But it can be a little bit more complicated than that in the industry. All right, so let's look at a few steps on how we liquefy nitrogen. First, let's say we have just nitrogen, 1 bar pressure, room temperature. That's cheap because you can get it from air. All right, but this time we're gonna compress this nitrogen at room temperature from 1 bar to 200 bars. This is gonna increase the temperature of nitrogen. Okay, because of this, you can see when pressure goes up, temperature goes up. All right, so we have a really hot and a high pressure nitrogen gas. This time we can use ice cold water, which is cheap, to lower the temperature of nitrogen back to a lower temperature. For example, over here it's just 0 degrees Celsius. That's not a problem, and this is cheap, just ice cold water. And then if we have some really cold nitrogen gas, we can further lower the temperature of this high pressure nitrogen gas to 120 K. So now you have a real gas, nitrogen gas, very high pressure 200 bar and low temperature 120 Kelvin. And now what do? We will do this Joule-Thomson experiment. We will allow the pressure of this gas to drop from 200 bars to 1 bar. And therefore, the temperature of this nitrogen gas will drop correspondingly by this much. So it's just basically this ratio, 0.247 times the pressure change. It's going to be roughly 50 K. Alright, remember over here we had 120 K and then we drop another 50 K. It's going to be 70 K. 70 K is below the boiling point of nitrogen. And therefore the nitrogen is liquefied. It has now a 1 bar pressure and a 70 Kelvin. Alright. By the way, how do we get this 120 Kelvin nitrogen gas, really cold nitrogen gas? It's just because after we make this liquid nitrogen, well, inevitably we will have some evaporation of this liquid nitrogen. It's going to produce a very cold nitrogen gas, which can be roughly this temperature, 120 Kelvin, or even lower than that. So we can use this very cold nitrogen gas to cool the 200 bar nitrogen at 0 degrees Celsius to like 0 degrees from 0 degrees Celsius to roughly 120 Kelvin. This is pretty cold. This is negative 150 degrees Celsius. So we have a diagram to show you all those steps. First we have nitrogen, room temperature 1 bar. That's boring. We compress it to actually after we compress it, we allow it to cool down to room temperature and 200 bars, and then we use ice cold water to further cool it to 0 degrees Celsius, 200 bars, and we use very cold nitrogen gas to further cool it to 120 K. It's very cold and 200 bars. The final step is the Joule-Thomson experiment. It's so-called isenthalpic expansion of the real gas. When the pressure drops, its temperature drops, and the temperature change divided by the pressure change for nitrogen is 0.247 Kelvin per bar. So going from here to here, we can make the temperature of this nitrogen gas below its boiling point, and then we have liquid nitrogen.